Hello and welcome to Intervals of Continuity. So in the previous video, we discussed what it meant for a function to be continuous at a point. And so now we're going to look at sort of this interval of points where a function is continuous. So again, we've seen what it means for a function to be continuous at a point. And now we want to study sort of all of the points where a function is continuous. So we are essentially looking for where our function is continuous. So if we look at the function graphed here, essentially we're looking for where there is a break in the graph. So our function we can draw without picking up our pen. We keep going, and then all of a sudden we stop, we have to pick up our pen. So we have a break. So we break at this point, right? And then we keep going, and we could keep going forever. So our function so the only break in the graph is at x equals 2. And we're continuous for all x less than 2 and for all x greater than 2. So if we put this in interval notation, our intervals of continuity we are looking from -infinity to 2, open interval, and then union 2 to infinity. The only place we are not continuous is at x equals 2. So now we have a series of functions. Our job is to find which of the following functions are find the intervals over which the following functions are continuous. So for a rational function, the only place where a rational function has a break or is undefined is when the denominator equals 0. So the rational functions are continuous everywhere except where the denominator, rational functions are continuous everywhere except where the denominator equals 0. So if we take our denominator We do not want the denominator equal to 0. So we don't want x plus 3 equal to 0. So we do not want x equal to -3. So just like the previous function that we were looking at, there was only one place where our function had a break. So in this case, we'll have what's called a vertical asymptote, our intervals of continuity. Will be from -infinity to -3, and then from -3 to +infinity. Next up, we want to study the function square root of 4 minus x squared. So just recall that even roots require the inside to be greater than or equal to 0. So essentially, we are looking for where on Earth our function is defined. So we are looking for where that inside is greater than or equal to 0. So we want to know essentially when is 4 minus x squared greater than or equal to 0. There are various ways we can figure this out. You could graph it, you can factor it and study what the function looks like. In this case, if we are essentially looking at the function negative x squared plus 4, we're looking for where that is greater than or equal to 0. So if we graphed that, now we have a y-intercept of 4, and then negative x squared plus 4 equals 0, at -2 and +2. So we're looking at our upside down parabola. If we wanted, we could factor this. We have negative x minus 2, x plus 2. Looking for where that is greater than or equal to 0. So this happens on the interval from -2 to 2. We get a little strange with the endpoints for a function that's defined on a closed interval. Sometimes we say it's continuous on the closed interval, and you just argue the endpoints just based off of one side, or you can say it's continuous on the open interval, since technically continuity, the original definition is that the limit exists from both sides. Right? So we'll just go with we're continuous from -2 to 2. So anything between -2 and 2, the limit exists and the limit equals the function value. Next up, cosine of x. Cosine of x is defined everywhere. And it's always connected. If you think about the graph, cosine just repeatedly goes up and down and up and down and up and down over and over and over again. So the interval of continuity is the entire real number line. So you could either write this as -infinity to infinity, or we could just write it as our fancy R for all real numbers. So that's sort of how we go about finding interval of continuity. Mostly, we're essentially just looking for where the function is defined. If it's undefined somewhere, or in case of piecewise, where we transition, check that the limit exists. So for non-piecewise functions, we'll do this in another color. So for non-piecewise functions, we are essentially looking for where the function is defined. For piecewise functions, we have to check sort of the breaks between the pieces. So check the transition from each one piece to the next. And then we also have to watch out for places where the function is undefined. So I should specify where we check the transitions. What we're looking for is we're looking that the limit exists, right? Make sure the left and right side match, and that it equals the function value. And then watching for places where the function is undefined, that can occur both at the transitions and within the individual pieces. So that's just basics for finding intervals of continuity.